Hello, I'm back, ladies and gentlemen. We're going to talk about components in three directions now, in three dimensions now. So the vector can be decomposed into three different directions: ax times I hat, ay times j hat, az times k hat. The I hat, j hat, and k hat tell us the direction. Ax, ay, and az tell us the magnitude. And here's how it works. So here we have the vector A, and we decompose it into its three components: AX, AY, AZ. And this A prime is the projection of the vector down on the XY plane, by the way. That's what this is showing. That's what this little diagram is showing. So then here's all the I hats and J hats put in. The magnitude of A, the square root of the squares of the three different components. There are direction cosines. If you take A dot K hat, that will give you the direction cosine times the magnitude of A against the z-axis. Most people don't find them very useful, so you can read about that in the book. I'm not going to talk about them. Okay, most people will use what are called spherical coordinates, r, theta, phi, where you look at the angle between the vector and the z-axis, and that would be A cosine theta would be the magnitude of AZ. A prime then is, excuse me, got these mixed up. Let's fix it. So this would be phi. Switch the thetas and the phis. Watch out though, because some people call this angle theta, and some people call this angle phi, by the way, instead of the way your book does it. So theta here, phi here, phi here. There we go. Okay, so I'll swap the thetas and the phis. So AZ equals the magnitude of A times cosine phi. A prime is the magnitude of A times the sine of phi, the sine of this angle. That's A prime. And then you multiply it by the cosine of theta to get AX, and you multiply the length of A prime, A sine phi, times the sine of theta to get AY. And I better clear the marks off so you guys don't keep seeing them. Here's an example. So position is a vector also. And this diagram tells us the position of point A and point B. So we look at A being how far in the x direction do we have to go? Well, we have to go 4 meters in the x direction, and then 2 meters in the y direction, and then down 6 meters, negative 6 meters in the k direction. The vector B, we have to go 4 meters plus another 2 meters in the x direction, 6 meters, and then back 1 meter in the y direction, and then we go up 4 meters in the z. So A minus B will give, that's from from here to here. The tail will be here to here. Okay. So the x direction, I take that back. Let's see. B plus, I'm sorry, wrong direction. Tail is here, point is here. So I'll go ahead and mark that. So this is A minus B. Okay. We know it's A minus B because if we take B plus this, we get A. And we can see that that's tip to tail. B plus the result equals A. So we know that's true. So 4 minus 6 is negative 2. 2 negative 1 is positive 3. Negative 6 plus 4, oh, excuse me, negative 6 minus 4 is negative 10. If we were to start at point B, how would we get to A? Well, we'd have to go back 2 meters to get to the same x coordinate, so that's negative 2. And then we'd have to go positive 3 meters to get to the correct y coordinate. This plus this, we'd have to go positive 3 meters to get to the proper y coordinate. And then we'd have to go down 10, 4 and 6. We'd have to go down 10 to get from B to A. Okay. Oftentimes we use ordered triples. A equals 4 to negative 6 with the units in parentheses at the end. Or we may do this, label a point with an ordered triple. Come on, there we go, there it goes. And I better clear out the screen again just so you guys, it doesn't keep following. Here's an example where a man is pulling on the rope with a force of 70 pounds. Oops, why did it go? Okay, there we go. So we're going to want the unit vector in the r direction. So from A to B, pulling in this direction. So he's pulling, here's 12 feet in the x direction, negative 8 feet in the y direction, and negative 24 feet in the z direction. We create a unit vector that is a directional vector pointing from A to B. That's what this is all about, right here. And since it's not I hat, j hat, or k hat, we just label it E. And we may subscript it. Using Excel, so we put R in here, F in here, figure out the magnitude, and it's the square root of the sum of the squares of the 3 components. So we take these 3 components, square it, and then take the square root of the sum of all these squares to get the magnitude. And we create, so that gives us the magnitude of R, and we create the unit vector. 12 divided by the magnitude is the unit vector in the x direction. Negative 8 divided by the magnitude is the unit vector in the y direction. Negative 24 divided by the unit vector is the, divided by the magnitude is the unit vector in the z direction. And then you can dot product. I take that back. You don't dot product. You just take a simple product. You take the unit vector in the x direction times the magnitude of the force to get f sub x, 30. Unit vector in the y direction times the magnitude of the force to get negative 20. So G2 is over here, by the way. That's the unit vector in the y direction. And then the unit vector in the z direction times the total force gives you the z component of the force. So these are the components of the force. 30I hat, negative 20J hat, negative 60K hat. Here's a sanity check. The sum of the squares of 30, negative 20, and negative 60, just to make sure our magnitudes wind up at the same place. Just a sanity check. Okay. We'll pick up the dot product in the next video, video number 3.